Hello, today we're going to talk about phase difference in waves and how to calculate it. The first thing that we must understand is that waves are usually represented in two types of graphs: amplitude in meters versus distance in meters, and amplitude in meters versus time in seconds. Um, Graph A, both have the same thing in the y-axis, the meters, but one has distance in the x-axis and the second one has time in the x-axis. Be careful because even though they look the same, they're two different kinds of graphs and they're measuring two different types of things. They're reflecting two different types of things. We already know from past videos that in the first type of graph, amplitude versus distance, we can calculate the wavelength. Okay, so the wavelength is the distance between two equal points in the wave. Remember that, for example, in the origin, the wave goes from negative to positive. In point 2, the wave goes from positive to negative, so it's not the same point. The next point, which is equal, is point 4. So we can see here that the wavelength would be 4 meters, but the best way to calculate it, we always recommend to do it between two crests because they're always easy to detect. So the distance here between two crests is 5 minus 1, so that's 4. So we can see in both points that the wavelength is 4 meters. Okay, so between these 2 points or those 2 points, the wavelength is 4 meters. Okay. In the second graph, what we can calculate is the period, which is the time it takes for a complete oscillation. And again, if we look at the graph, sorry because I've drawn them by hand, but if we look at the graph, a complete oscillation again would be done in 4 seconds. So the period here would be 4 seconds, and the frequency, which is the inverse, would be 1 divided by 4 hertz. Okay, so we've already seen that in previous videos. What we want to see now different is how to calculate the phase difference between either points or two different waves. Okay, so I'm already going to give you the result. So the phase difference in this sort of videos is going to be the difference in distance divided by the wavelength and multiplied by, if you want it in degrees, 360, and if you want it in radians, that'll be 2 pi. So it'll be either or, because the phase difference is measured at the same as degrees. Okay, and if we're looking at this type of graph, the phase difference is going to be the difference in time versus the period, sorry, multiplied again by either 360 or 2 pi if we want it in radians. Okay, so that's, if you don't want to look at anything else in the video and don't want to know why, you can stop here. Although we will look at some examples and I will explain why these formulas work like this. And I don't like to remember formulas, I like to understand it so I can remember the formulas easier, in an easier way. Okay, so we're talking, the first thing that you have to understand is that when a wave does a complete oscillation, okay, so for example here from point 0 to point 4, we can consider a circle going, we can consider it similar to a circle going through doing a complete circle. Okay, so that's from 0 to in degrees we would say 360 degrees or 2 pi. Okay, so we consider that in a wavelength it's doing a complete oscillation, so it's going to do 360 It's going to travel through 360 in its phase, okay? 360 degrees, or 2 pi, okay? So when it goes half a wavelength, that's going to be obviously 180 degrees or pi. And if we do a quarter of a wavelength here, that's going to be 90 degrees or pi halves. Okay, so what we're basically doing is we're considering that a complete oscillation is 360, and then we're uh, following that reasoning to consider that half oscillation is pi or 180, a quarter is pi halves, etc. Okay, so let's so for example, let's consider again the wave that we had, which was something like this. And if we consider points in the wave, we can consider, for example, this is point A, point B, point C, and let's consider D and E, for example. Okay, so point A and B have a phase difference. Sorry, as we said before, between point A and point C, as it's a complete oscillation, there's a phase difference of 360 degrees or 2 pi. Okay, because here, over here, that is a whole wavelength. Okay, between point A and point B, because of the same reasoning, that is half a wavelength. So we have 180 degrees of phase difference or pi as a phase difference, okay? And if we consider from A to D, so that's 90 degrees, as this is pi quarters, okay? Or sorry, that's lambda quarters, that's the wavelength divided by 4, and that's pi halves, okay? And if we consider the last one, which is from point A to point E, that's pi halves, pi, 3 pi halves. So 3 pi halves, or 90, 180, 270. Okay, so it's fairly easy to calculate the difference in phase in between points of a wave, as long as we consider that the wavelength is 360. So we always have to, once we see these graphs, calculate what the wavelength would be, and then consider that that is 360 or 2 pi, and divide all the distances into its fractions. Okay, so imagine we then have another wave, which instead of having the crest there, is going to have the crest, let's say, here. No, let's do it here. Okay, so it's going to be displaced. Okay, so what do we call the phase difference? Well, the phase difference is going to two waves have a phase difference when they occur at different distances or spaces in time. Space in distance or spaces in time. Okay, so in this type of graph, the two waves are happening. The two same points are happening at different distances in time. Okay, so they have a phase difference, which is this. Okay, so how do we calculate that phase difference? Again, what we're going to do, it's the same as this one. Okay, so again, what we're going to do is we're going to as we consider in a phase difference, it's always going to be related to a reference. So we will take the blue wave as a reference. We can do it either ways. Let's use the blue wave. And we will look at the wavelength of the blue wave, which we've already seen that it's 4 meters. And so we could divide, we could do a ratio, and we can consider that a wavelength is to 360 degrees as the phase difference, which is, as you can see, as you see, it's from 2 to 1, so it's 1 meter, is to the phase difference that we want to calculate. So that'll be that. Okay, so I'll repeat that again. Okay, if we have called we have said that our lambda is going to be 360 degrees. Okay, well, we can do a ratio which is going to be our lambda, which is 4, equals 360 degrees, just as 1, which is our meters, this is 1, is our phase difference. And if we put theta as the subject of equation, we get 1 divided by 4 times 360. Okay. If we did this with letters instead of numbers, we can see that lambda is going to be 360, just as our phase difference. Just as the distance is to our phase difference, which is in degrees. So if we put theta as the subject of the equation here, we get this formula, which is only a proportion, as you can see. It's a change of units. We're changing units from the known ratio that we know our wavelength difference into 360 to the phase, the distance here between the two waves into our phase difference in degrees. Okay, so that's the formula that we had over here. Okay, in degrees. If we did this instead of 360, if we change that for 2 pi, we would get the answer in radians. Okay, so in the example that we're looking at today, our distance was 1 meter, our wavelength was 4. So we divide that 1 divided by 4 and multiply by 360, and that's 90 degrees. So our phase difference is going to be 90 degrees. Okay? And you can do that in any kind of wave. Let's do another example very quickly. So if we have this, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and we draw. Let's do the same amplitude 3, but instead of now being like this, we will double that. Okay, so now it's going to be no, it's going to be 4 there. Okay, so it will get its maximum at 6, and then 8. Okay, so if we had this wave, and then again we had this wave over here, for example. No, let's do it here. So that's going to be every 2. That's going to be like that. And and that was 4, so that'll be 7. Okay, so what would be the phase difference? And this is in meters. So what would be the phase difference in this case? Okay, so let's look at the blue wave. Let's calculate its wavelength. So a complete oscillation is 8. So the wavelength is going to be 8 meters. Okay, so if that's going to be for us 360 degrees. Okay, so let's calculate now the distance here in meters. And that's going to be 5 minus 2, which is 3 meters. Okay, 5 minus 2 is 3 meters. Okay, so if we can do either, I'll do it two ways. We can do the ratio, so that's going to be 8, which is our wavelength, is 360, just as 3 is theta. Okay, so then we get theta equals 3 divided by 8 multiplied by 360. Or we could do it with a formula, change in distance, wavelength, 360. Okay, we'll do that, yeah. Okay, so if we calculate, the change in distance was 3. Okay, so if we do that, 3 divided by 8 and multiply by 360, so our wavelength, our phase difference is going to be 135 degrees. If we did that, 3 divided by 8 multiplied by 2 pi, so that's 6 divided by 8, that's um, that's 3 pi fourths. Okay, okay, so that would be the phase difference. So this is easy. Once we understand how to do it, we can either use the formula or the proportion and calculate it when we have uh, uh, amplitude versus distance. What happens if we have an amplitude versus time? We can do the same thing, but now instead of calculating the wavelength, we're going to calculate the period. Okay, so let's get the blue wave here. And if you look at the blue wave, we don't have a complete wave, but we can consider that this wave would go up here, and this is going to be half of the 3 is going to be half of the period. Okay, so we already know here that the period in the blue wave is going to be 6 seconds. Okay, so let's try and see what the difference in time there is between one wave and the other. We can use the crests, but as you can see, the crests are between two grid lines. So let's look at our any other point, and if we look at this point which goes from negative to positive and negative to positive, we can use it. Okay, so if we can consider that this point over here is each grid line is 2, so that's 1.2. So the difference is going to be 1.2 seconds. Okay, so again, we could consider that a whole period is 360 and do a proportion again, a ratio, or we can just use again the formula that, as you see, both ways are going to, we're going to obtain the same thing in both ways. The difference in time, which is 1.2, is to the wave, to the period, and then we multiply by 360, or 2 pi. 1.2. So in degrees, we would obtain 1.2 divided by 6 multiplied by 360 at 72 degrees here. And if we look at the in the, if we do this in the calculator, that's 2 pi fifths. Okay. Okay. So if we have an amplitude versus time, we have to calculate the period and then calculate this distance between the 2 points, and that's going to be the difference in time. And we can consider that the period is to 360 degrees, as that difference in time is going to be to our phase difference. And then we can calculate that phase difference that way. Okay, so as you see, a phase difference is just a displacement in the x-axis, either in space or in time, of a wave or of different points, and we can calculate it with a ratio, just considering that the whole wavelength is 360, or the period is 360 degrees, or 2 pi, or we can use these formulas. You can remember these formulas I leave here for you, and just do some exercises and you'll see that it's very easy.